Yeah. So check out this arithmetic sequence here, right? I've got a 1, I got a 3, I got a 5, 7, 9, and then the dot 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 means keep going in that manner, right? What if I wanted to add these up? All right? And let's just call it up. Let's just add it to there for now. I'll cut off the sequence up to there. So I'm going to move this up, and let's add this up sort of by hand here. So if we're going to add this by hand, let's go quickly do it. Let's see here. 1 plus 3 is 4. 25. Okay, so we get 25 when we add this up. Okay, cool. Now, we also have a formula because this is arithmetic, right? And the formula says that the sum of the first 5 terms has to be 5 divided by 2, and then the first term plus the last term, which of course is 5 divided by 2 times 10, which is half of 50, which again is 25, which totally makes sense, right? All right. Next thing I want to ask you guys to do is I'm gonna sort of take this line away now for a second. Okay. This is an arithmetic sequence, right? So I am wondering if you guys could tell me what is the a sub nth term? How can I use the fast forward formula for arithmetic sequences to define what the a sub nth term is? Could you guys do that? Yeah. Okay, go ahead and do that. Tell me what is the best one of this. Do we all see that this sequence is nothing more than 2n minus 1? This is the way that we define the sequence. You guys agree with that? Yeah. Okay, so meaning that the fourth term would be 2 times 4 is 8 minus 1 is 7. So the fourth term is 7. Okay, good. Now, if I want to add up the sequence that's defined by 2n minus 1, so if I want to add this sequence up that's been defined by 2n minus 1, what would be the sum of the very first term with just by itself? What would that be? That'd be 1. I agree with that. What would be the sum of the first 2 terms? Well, that would be 1 plus 3, which is equal to 4, which is also equal to 2 squared. What's the sum of the first 3 terms? It'd be 1 plus 3 plus 5, which is 9, which is equal to 3 squared. Huh. The sum of the first 4 terms would be 1 plus 3 plus 4%, which would be 16, which would be 4 squared. Yes, so you guys are noticing something here, right? So what would be then the sum of the first 5 terms? Well, it'd just be 5 squared. Oh my God, which of course is 25, right? Okay. So it looks like the reason I'm doing this is because all of this seems to just add up to the number of terms you have squared. That's what it seems like, right? So 1 plus 3 plus 5 plus 7 plus yada yada yada, all the way up to 2n minus 1 is nothing more than n squared. So what would the sum of the first 10 odd numbers be? 100. What would the sum of the first 12 odd numbers be? 144. 144. Okay, so the question. No, the sum of the first 12 odd ones, right? Is just 12 squared.
The first 25.
Oh, the first 25. Ooh, what would it be? There you go. Okay, so the question then that I have for you is this. This is where this is going, okay? How do we know that this right here, this statement, how do we know that that is true for every single n that we could possibly think of?
It doesn't seem true though, because
we're going to use the principle of mathematical induction to actually show that this is true for every single n, all right? So let me explain what the principle of mathematical induction is, and then we're actually going to go back and prove that this, in fact, is a true statement. So here we go. Yep. Okay, so you're going to be given a statement about some positive integers n, and what I mean by that is like right up here, this right here, this is a statement, all right, of some positive integers n. So you'll be given something like that. So if you're given a statement about positive integers n, then 3 things have to happen. And I say if 1, 2, 3, then we can say something is true for all positive integers n. Here's the 3 things that have to happen, right? First, you have to show that n is true for n is equal to 1. Or show that your statement is true for n is equal to 1. You actually have to show it. You have to do the math and show that your statement is true for some n equals 1, the very first term of your sequence. You have to show it.
Oh, like.
The next thing you have to do is you have to assume that your statement is true for some n equals k in your sequence. So here's what I mean by that. So let's say I had the sequence, 1 plus 2 plus 3 plus yada yada yada. There's some k somewhere along, plus yada 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 up to n. So k is somewhere along in the sequence. You're assuming that this statement is true up to a k, the kth term. K is arbitrary. It's somewhere in the middle of 1 and n, somewhere between there. All right? So if you can show that it's true for the first one, you then assume it's true for some n equals k, then you actually have to prove that this is true, that your statement is true for the very next term in the sequence. So if I'm at the kth term in my sequence, what's the very next term going to be? K plus 1. Very good, you guys. K plus 1. So if you can do these 3 steps, okay, then you can say that your statement, your original statement, is true for all positive integers n. So that means for all. And the fancy z is the positive integers, and then n are the ones that you're working with. Okay, here we go. We're going to use the principle of mathematical induction to show that 1 plus 3 plus 5 plus all the way up to 2n minus 1 is nothing more than n squared. So before we do this, though, I want to sort of break this down and show you exactly what all the parts mean. So what does this part mean up here? The 1, the 3, the 5, what does all that mean right there? What do we call those things? Those are just the terms, yeah. The terms or the sequence that we have, right? What do we call this part right here? This 2n minus 1. What is that part? Yeah, this is the a sub nth term. Exactly. What do we call this over here? This n squared. Yeah, this is the sum of them all, right? So we're saying the sum of the sequence up to 2n minus 1 is nothing more than n squared. You got to know what all the parts are, okay? So here we go. Step number 1, we're going to show that this is true for n is equal to 1. So what do I mean by that? I mean, if I plug in a 1 on the left-hand side, is 2n minus 1 the same thing as 1 squared? Of course it is. 2 minus 1 is equal to 1. Yep, 1 is equal to 1. Awesome. Step 1 is done. So I just showed through algebra that this is true for when n is equal to 1, right? Okay, awesome. That's my very first step. My second step then is to assume that this is true for some n is equal to k. All right, so if this is true for some n equals k, then we have this statement here. We have 1 plus 3 plus 5, that's right? Yeah, plus yada, 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 plus up to 2k minus 1. Because I'm assuming that this is true up to some k. No, it's a k. Because k is some point right here, remember?
So does that mean like 2k? Oh wait,
Yeah.
that's exactly what you're trying to.
Yeah. So what that's going to equal on the right-hand side, it's going to equal k squared. That's what we're assuming. We're assuming that 1 plus 3 plus 5 plus all the way up to 2k minus 1 is equal to k squared. That's the setup. Okay? Then step 3, this is when it all comes together. We actually have to prove.
What's the point of step 2? I don't understand.
So step number 3 is we're going to prove that this is true for n equals k plus 1. Now here's why I want you to write this out every single time. So we have this 1 plus 3 plus 5 plus blah 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 plus 2k minus 1. What is the next term?
2k.
2 times k plus 1 minus 1.
Oh, yeah.
All right, don't forget to distribute that.
Oh.
Okay? Now, on the right-hand side, what are we replacing with? It's not k squared anymore. What is it? It's k plus 1 squared. Yes, there we go. This is where the algebra comes into play. This is why you need that k in there, because it's any arbitrary point up to a certain point in the sequence. Now, here's the really cool part. Somebody out there, I'm going to put this box around this information right here. Can someone tell me what that actually equals? Which is why you need step 2, Tommy. Yes, very good. It will always equal k squared. Or it will always equal the right-hand side of step number 2. That's the cool part about it. So all this stuff that I put in the box, that's equal to k squared. You guys deal with that? Yeah. Yes, yes, very good. So check it out. I still have this. Let's go ahead and distribute this. 2k is going to be, that's just 2k, right? And then 2 times the 1 is a plus 2, and then I have a minus 1. And we're trying to prove that that's actually equal to k plus 1 squared. If the algebra works out, then we've proved it for any k possible, right? So check this out. I have a k squared plus a 2k. 2 minus 1 is just 1. Is that equal to k plus 1 squared? Of course it is, because we can factor this to k plus 1 times k plus 1. And we're trying to prove that that's equal to k plus 1 squared. Oh my gosh, check it out. K plus 1 squared equals k plus 1 squared. Therefore, our statement is true for all positive integers n. Okay, here we go. We're going to use the principle of mathematical induction to show that 1 plus 2 plus 3 plus all the way up to n is equal to n times n plus 1 over 2. This is the same problem that we did when we came up with adding the numbers from 1 to 100. Remember that? Yeah. How do we prove that this is actually true for any n that we want? Okay, so step number 1, we're going to show true for what, you guys? Wow. For n equals 1, you got it. For n is equal to 1. So I say this. 1 is equal to 1 times 1 plus 1 divided by 2. Yep. 1 is equal to 2 over 2. 1. Check. Done. Awesome. It's true for the first one. Okay. Step number 2. We're going to assume that this is true for n is equal to k in our sequence. So what does that mean? That means 1 plus 2 plus 3 plus yada 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 plus k must be equal to k times k plus 1 over 2. Everybody on board with that step? Okay, step number 3. We're now going to show... Oh, thanks. Prove. Good job. We're going to prove that this is true for n is equal to k plus 1. So let's write it out. What does that look like? It looks like this. 1 plus 2 plus 3 plus dot 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 plus k plus, what's the next term, you guys? K plus 1. Very good. K plus 1. Is that equal to k plus 1 times k plus 2 all divided by 2? Okay, now where did this k plus 1 come from? Because that's the next term after k. Where did this k plus 2 come from?
You plug that in.
Yeah, k plus 1 plus 1 is k plus 2. All right? So, somebody out there tell me, what is all the stuff in this box equal to? It's equal to that right there. So I can replace this and say, okay, k times k plus 1 over 2 plus a k plus 1 is equal to, this is what we're trying to show, k plus 1 times k plus 2 all divided by 2. Okay, everyone, Tommy's got a pretty good answer, wants to share it. So what do you got for us, dude?
So first you have to be able to add those.
Yes.
So you have to make the common denominator.
Yeah.
You have to multiply the top by 2 and
So
the bottom by 2.
2 over 2, right?
Yeah.
Very good.
And then you distribute
Okay.
on each side of the...
So you got k squared plus k plus 2k plus 2 all divided by 2? Is that what you do?
Yeah, and then you add like term to that, and then you just factor it.
Mm-hmm. So then I factor this. So we get a k plus 1 times a k plus 2 all divided by 2, which is exactly what we were looking for. So therefore, ladies and gentlemen, it can now be stated by the principle of mathematical induction that 1 plus 2 plus 3 plus plus n is equal to n times n plus 1 over 2 for all positive integers n. All right, this one says that the sum of the first n squared terms is n times n plus 1 times 2n plus 1 all over 6. All right, we got some algebra to do on this one. So first, what's the very first thing we're going to do?
Show that n equals 1.
You got it. Show it's true for n is equal to 1. So is it true that 1 squared is equal to 1 times 2 times 3 divided by 6? Yep, it sure is. 1 is equal to 1. Check. I like step 1. Everybody likes step 1. No big deal. Okay? So step number 2, so we showed it. Now we're going to assume that this is true for up to some n is equal to some k. So we say this, 1 squared plus 2 squared plus 3 squared plus ... k squared is equal to k times k plus 1 times 2k plus 1 all divided by 6. That's our assumption. On board? All right, sweet. Then, third one, we got to prove that this is true for what?
N equals k plus 1.
For the next term in the sequence, right? So we write down and we say, okay, 1 squared plus 2 squared plus 3 squared plus ... k squared plus, now what do we do?
K plus 1 squared.
Very good. K plus 1 squared is equal to,
K squared.
this is going to be k squared, right? No. K plus 1 times k plus 2 times 2 times k plus 1 plus 1
Simplified it earlier.
all over 6.
Wait.
So then what does all this stuff equal?
K times K plus 1 times 2K.
Yeah, exactly. That equals k times k plus 1 times 2k plus 1 over 6. And then I have a plus k plus 1 squared. And I'm trying to show that that's equal to k plus 1 times k plus 2. This would be 2k plus 2 and then plus 1. So that would be 2k plus 3 all over 6. Okay, check my algebra, make sure this is true. So let's go over it really quickly. We noticed that there's a k plus 1 in each of those little terms, right? So I factored out a k plus 1. What would that leave me with? Well, let's use the distributive property to check. K plus 1 times a k and a 2k plus 1. That's all this information here, right? Do you see it algebraically? And then a k plus 1 times this stuff, well, that would be all this information there. So I like a factoring trick, right?
Yeah.
Okay, good. Now let's just work on the inside here. So I have a k plus 1. This is going to give me 2k squared plus k plus 6k plus 6 all over 6. That gives me a k plus 1. And then a 2k squared, was that plus 7k plus 6 all over 6? Ooh, can we factor that? Yeah. K plus 1.
Wait, now we can factor that out.
Probably 2k and a k.
Oh, wait, how?
6 and a 1? A 6 and a 1?
Oh,
A 6 and a 1?
Yeah.
I was like, 2 and 3 won't work.
I don't think there's negatives, so I think it's just a 6 and 1. You could put it
Yeah.
either way.
So, no, it has to be, I think it has to be 3 and 2.
Yeah, you can do k plus 2 and 2k plus 3.
Yeah, k plus 2 and 2k plus 3. Hey, it's exactly what this says over here.
Wait, can you go
What?
Look at that. K plus 1, k plus 2, 2k plus 3. Look, there it is. That's awesome.
That good.
Wait, can you go back up?
Okay.
Yeah, here.